Hello everyone, welcome back. So in today's video, we are going to be taking some problems from mechanics. So the first problem is from fluid mechanics. So here we have a block whose mass is given to be capital M and it's rested on a frictionless floor. So there is no friction present anywhere and it contains a curved channel. The channel is designed so that when a horizontal jet of fluid is aimed at it, the fluid is redirected 90 and shoots straight up. Okay, so a cross-sectional view of the box is given to us. And it has a curved pathway through which fluid can enter and leave the container. And obviously, as a result, the block will start moving. Now it's given that the flow of the jet is q kgs per second and has a velocity of v meters per second. So assuming no gravity and ignoring any viscous effects, so we have to mainly figure out the speed as a function of time. Okay, and then in this option they're asking us about the power delivered by the fluid to the block at t equal to 0. Okay, so this can be answered very easily because initially the block was at rest. So now the power is just the dot product of force and velocity. So as the block is at rest, initially the power delivered by the fluid will be 0. So now we just have to find the speed as a function of time. Okay, so for that, let's first draw an FBD. There were a few information that was given to us. So firstly, the mass flow rate of the fluid was given to be Q and the velocity of the jet was given to be just V. Okay, and these two are obviously constant with respect to time. So now as we want to figure out the velocity as a function of time, we want to figure out how much force does the fluid impart on this box. For that, what we'll do is we'll take a simple case over here where we have some kind of a vein through which fluid is flowing. It's a very similar situation to what we see above. So fluid is entering through this cross section and it is leaving through this cross section. Okay guys, so now what I'm going to do is I'm going to take the entire fluid inside the tube as my system. So let's say the mass of the entire fluid inside the tube is some small m. And another thing is that the average velocity of the fluid flow is going to be a constant because the area of cross section is not changing. Okay, so now what I'm going to do is I'm going to take a small dm mass element, which is over here in blue color, and I'm going to say the length of this element is v dt. Okay, and let's say the mass of this particle is dm. Okay, so now what will happen is in the next dt seconds, the particle will obviously cover a distance of vdt, right? Which means this dm mass will be completely inside the tube, and obviously as a result an equivalent mass of dm will be pushed out of the tube. So let's draw the situation after dt seconds. So this dm mass is now completely inside the tube, and the equivalent and the same dm mass from the other side is completely pushed out. Okay, so now what I'm going to do is I'm going to take this dm mass and the fluid present inside the tube as my system. Okay, so now let's try to write the initial momentum of the system. Okay, which is basically the momentum of this part, which is the momentum in this situation. Well, the momentum is just going to be sigma mi vi of all the particles, right? But here if you observe something, the net momentum of all the fluid present inside the tube, they are identical in both situations, right? Because there is no difference in what happens inside, right? So if I take a random particle mi inside the tube, it in this case, let's say it is moving with vi, so here also it will still move with the velocity of vi. So we can say that the net momentum inside the tube is the same in both the cases. So I'm just going to call the momentum due to the fluid inside the tube as just p vector. Okay, because it is going to get cancelled out when we take the change in momentum, so it'll be clear in a bit. So other than the fluid present inside the tube, we have this dm mass over here, and its momentum, if you observe, it is the mass of the particle times its velocity vector. Okay, so now just for the sake of explanation, I'm going to take it as v1 vector. Okay, so the mass of the fluid entering, I'm calling it as v1. Okay, so this is the initial momentum. Now let's talk about the momentum after dt seconds. So it is using exactly the same idea. The momentum of the fluid inside the tube is still the same as p vector. Now our dm mass, the change here is that now the dm mass is ejected out with a velocity of v. So, and let's say the exit velocity for a second is v2 vector. So its final momentum is dm times v2 vector. So if we observe the small change in momentum dp, it is nothing but dm multiplied by v2 vector minus v1 vector. So what we did so far is we figured out the small change in momentum in our fluid system, right? So the small change in momentum of the liquid, I can also say, is the impulse applied on the liquid, right? So an impulse, I can write it as f times dt. As we are talking about a small time interval dt, right? We can say it is f times dt, where f is the total force acting on the liquid, right? So when we write impulse, we write impulses due to all the forces. So, okay. So this f vector is going to be the net force acting on the fluid body, and that times dt will give us the impulse acting on the fluid. Okay. So from here, the force acting on the fluid, f vector, we get it as dm by dt times v2 vector minus v1 vector. So here v2 vector is the exit velocity and v1 vector is the inlet velocity, and their vector difference times dm by dt gives us the net force acting on the liquid. Okay, so now by Newton's third law, we can just say that the force on the vane is going to be just minus f vector, which is minus dm by dt times v2 vector minus v1 vector. Okay, so now let's say the vane had some horizontal velocity, let's say u vector. Okay, in this case, what we are going to do is we are going to write all the velocities relative to the vane. So how will we do that? We'll just subtract u vector from the individual velocity. So the inlet velocity here, we took it as v1, right? With respect to the vane, the fluid is coming in with a velocity of v1 minus u vector. Okay, so now the vane will appear to be at rest, and now once again we can use the same impulse momentum logic, and we can figure out the net force imparted on the vane. Okay, and as the area of cross section is not changing, the exit velocity will also be v1 vector minus u vector, right? Because of the continuity equation. Okay, so now here there might be a confusion for you guys, because we know the vane is going to be accelerated, right? Because there is some force acting on the block, it's going to accelerate. So how are we considering u as a constant here? And the answer to that is, if you guys remember the derivation, we're only applying impulse momentum in a small time interval of dt, right? So in this small time interval of dt, we can consider u to be a constant. Okay, so with that, now we can move on to the current problem. Okay, so the inlet velocity of the fluid was given to be small v, and it's a constant. Okay, now let's just say at some arbitrary time, the box was moving with a velocity of v capital M. Okay, so once again we'll write the velocity of the incoming fluid with respect to the box. So we'll subtract vm from v. So the fluid is incoming with a velocity of v minus vm. Obviously in the frame of the box is at rest. So the fluid that is entering with some speed must leave with the same speed, right? So the exit speed must also be v minus vm. So we determined earlier that f vector on the liquid is dm by dt times v2 vector minus v1 vector. This is also a very important point here, guys. Dm by dt, it's not the volume flow rate of the fluid with respect to ground. Okay, it is in fact the mass flow rate with respect to the frame of the container. Okay, and this again goes back to our derivation that we did over here. So here initially we worked with the case that the vane was at rest, and so we concluded that in a time of dt, dm mass enters the vane. But if the vane itself is moving, then you guys can just imagine it. If the vane itself, let's say, is moving to the right, then now some mass less than dm will enter in dt seconds. Okay, so obviously the velocity of the vane has a role to play here. So here dm by dt once again is with respect to the frame of the box. Okay, so this is going to be rho times, let's say the area of cross section of the jet is a, and the relative velocity with which the fluid enters, which is v minus vm. Okay, so the formula I applied is just dm by dt equals rho av, which is a pretty simple result. So if we have a fluid that is moving with the velocity of v in some area of cross section a, then in a time of dt it moves a distance of v dt. So the mass dm in this volume av dt is going to be rho. In this small volume is the density of the fluid times its volume, and the volume of this part is a times vdt, right? So from here dm by dt, we directly get it as rho av. Okay, so the rho av is done. Now if you observe, it is the exit velocity minus the inlet velocity. So the exit velocity is v minus vm in the j cap direction, and the inlet velocity is v minus vm in the I cap direction. So I can take v minus vm common, right? And this is just going to be j cap minus I cap. So this is the force that is acting on the liquid. The force is acting on the plus j cap and minus I cap. Okay, which we can easily see by intuition as well. Initially the fluid was moving towards the right, and now finally it was made to move in the upward direction. So its horizontal momentum was destroyed, meaning there was a force applied on it towards the left. Okay, as we can see, which is in the minus I cap direction, and it was given a momentum in the plus j cap direction, right? And hence the force in the plus y direction. So this is basically the force that acted on the liquid. So the force on the body, force on capital M mass, is just going to be the negative of it. So I'm just going to consider the x component of it, because we are interested in the x direction motion. So that will just be rho a v minus vm squared, v minus vm squared. So this is the final force that acts on the mass capital M as a function of vm. Okay, so here if you observe, initially vm was 0, so the force is rho av square. Okay, but the force keeps on decreasing as the block moves towards the right? So now once we have the force in the x direction, now we can write it as the mass times the acceleration, which is dvm by dt. So now it's just a variable separable form. Okay, so at time t equal to 0, the block was at rest, so we'll set it 0, and we need vm as a function of time. Okay, so this is what we get. So now what we can do is we can send this v to the other side and write this as, now guys, initially the dm by dt of the fluid was given to be q, which means I can write q as rho av. Okay, so this is going to be qt by m. So now in the options, guys, if you observe, they've mentioned rho times q instead of qt, right? Because if it was dimensionally accurate, then qt would be the dimensions of mass. So here what they must have meant is q is the volume flow rate, which means q is in meter cubes per second. Okay, so anyways, so if I take q to be the volume flow rate, then that would be just a multiplied by v. So this is going to be rho q t by m. Okay, and once you solve it, you'll get the velocity as a function of time, uh, as this particular function, which corresponds to option B. So the answer to this question is option B and C. Okay. Okay, so now the thing is, if they ask the value of power delivered at some other time, okay, then what you can do is you can figure out the force F at that instant, right, which was actually rho A v minus vm squared. Okay, and just dot it with the velocity of the vane, which is vm. Okay, okay, and then you can figure out, and that way you can figure out the power delivered at some other instant. Okay, so that was it for this question. Now let's move on to the next one. Okay, so this is problem number 2, and here we have a ring whose radius is small r. So this is the ring, and its mass is 2m. So the mass of the ring is 2m. It rests on a rough circular track of radius capital R. A small point mass of mass small m is mounted on its periphery. If friction is sufficient to avoid any slipping, then the minimum ratio of small r by capital R. Okay, so it might not be clear what this question is trying to ask. So basically what is happening is, we can see this is a point of equilibrium, right? So if you don't touch it or disturb it, it will stay in this position. But let's say if you disturb it from the equilibrium position and you try to roll it such that it reaches this position. So now there might be two possibilities here. It can either roll away, right? So meaning it is a position of unstable equilibrium, or it can come back. So we want it to be a stable equilibrium. Okay, that is, if you disturb it, we want it to come back. So if that's the case, then they want you to tell the minimum value of small r by capital R. Okay, so that's basically what the question is. What is the minimum value of small r by capital R? So this position is a point of stable equilibrium. Okay, try to draw a very good diagram and try to solve it. Okay, so getting on with the solution. So this is a diagram of the situation, guys. So we have, so the track radius is capital R and the radius of the small ring is smaller. Okay, so the first thing we need to note here is that we are only talking about small displacements from the mean position. Okay, so now let's say we displace the ring in the middle by some angle. So I'm exaggerating the displacement to explain the question. So now I'm gonna hide our original ring. Okay, so now let's mark a point on our ring. So initially when it was at the mean position, I'm going to call the top, I'm going to mark the top point of the ring with a red dot. Okay, so now obviously we rolled the ring a little bit and we brought it to this particular position. Let's draw a line to the center. Now guys, obviously the ring, okay, so now the red point won't be at the top anymore. It must have rotated by some distance. So now let's say the red point is somewhere over here. Okay, so now this is very important, guys. Okay, so now if you observe this line over here, which connects the centers of the rings, rotated by some angle. So I'm going to call this angle as theta. Okay, so theta is the angle which the line OC rotated by. Okay, so now the thing is, the ring that is kept on the track must also have rotated by some angle phi. Okay, and that's the reason why the red point moved on the ring. So now this is another important point. This is not the angle phi. Okay, and the reason for that is you have to measure it with respect to a fixed axis. Okay, initially if you observe, if you draw a vertical line through the center, the red dot is right on the vertical line. Let's just measure it with respect to the vertical line. So initially the red dot was on the vertical line. Now it must have rotated by an angle of, let's say, phi. Okay, so theta and phi are our two angles. Phi represents the rotation of the disk about its own axis, and theta is the angle by which line OC rotated. Now why did I write this red dot? It's so that I can see where the mass, it's because if you observe, there is a mass small m here. So I want to track its position. So that's the reason why I marked it with a red dot. So now coming back to the question, we have released the disk. Okay, so in this particular situation, we want the alpha of the ring to be counterclockwise. Only then it will come back, right? So we want to ensure that the alpha, or phi double dot, okay, which is basically alpha, I can also write it as double derivative of this angle phi, right? Okay, and and once again we want it to be counterclockwise. Another fact is that the disk is pure rolling on the track. So here, as the disk is pure rolling, we can take the help of the instantaneous axis of rotation. So I'm going to call this point as point I, and initially I was over here, right? So okay, so now this is the part which is going to be a bit annoying. So I want you to pay close attention to the diagrams. Okay, so now as we want to determine the alpha of the rigid body, we want to figure out we have to choose an axis and apply tau equal to I alpha, right? So the best point here is definitely the instantaneous axis of rotation, because we don't have to bother about the friction force, right? If you take the center of the bigger disk, you'll have to take into account the friction force, which is going to be a pain. Okay, so in the instant center is the point that we're choosing, and with respect to this, we have to calculate the torque. Now what are the forces which we have to care about? We have to care about the 2 mg of the circular disc and we also have to care about the mg of this point mass, which means we want to figure out the horizontal distance between C and I and this small m mass. Okay, so that's where the now coming to the first assumption that we made, that the displacements here are going to be small displacements, or basically this angle theta and phi are very small angles, which means actually two things. First is I can write this distance cc dash as the using the arc length formula. So I'm going to write it over here. cc dash, I can write it as capital R minus small r times the angle theta. Okay, because this distance OC is capital R minus small r. So that times this angle theta will give us the distance cc dash. This is only applicable if the angle theta is very, very small, right? Is very small. And the second thing is that from a diagram, we see that this is not a horizontal displacement, right? It has some horizontal component and some vertical component. But the thing is, we'll ignore the vertical component, and we'll say that cc dash is actually a horizontal displacement. Now, okay, so we can I can also explain the reason for that real quick. So if you so this distance was capital R minus small r times theta. Okay. Now the thing is, you can very easily prove that this angle over here, right, is going to be theta by 2. Okay. So basically these two angles are pi by 2 minus theta by 2, which means if you draw horizontal here, this angle is going to be theta by 2. So now if this angle is theta by 2, the vertical length, you can basically write it as r minus r theta square by 2. So if you observe, the distance cc dash and the horizontal distance is approximately just capital R minus small r into theta. So now here, if you observe, the horizontal distance is actually first order in theta and the vertical distance is second order in theta. So it means so if we say this is tiny, this is even tinier, like it's very tiny, right? So if we are saying that this itself is tiny, then this is going to be even tinier. Okay, so that's the reason we can treat the distance cc dash as horizontal. Now the thing is, if some of you guys actually went the energy route and wanted to write the potential energy change, then you would have to consider this this second order term in the potential energy, right? So for the mg delta h term, you would have to use this. Okay, so anyways, we'll be treating the displacements as horizontal. Okay, so once again, this distance cc dash, we can just treat it as horizontal. So what I'm going to do is just for clarity, I'm just drawing it as horizontal. Okay, so this distance, once again, I'm still considering it as cc dash, and I'm going to say it is capital R minus small r times theta. Now this distance over here, which is the distance of the point mass from this vertical line passing through C. This is very easy to figure out. It will be the radius of the small disk times this angle phi. So this is just going to be R5, right? And once again, it's because phi is very small. Okay, so now we also need the distance of I from the vertical. That is also very easy to figure out because the point I is at a distance of capital R from O. So it must have traveled. So the distance traveled by I is going to be capital R times theta. But once again, we are going to treat it as a horizontal displacement. Okay, a horizontal displacement of capital R theta. Okay, so now we have all the distances that we need. So now we can just move on to balancing the torques. So once again, with respect to I, we want the angular acceleration to be counterclockwise. Okay, so if you observe, okay, so now guys, this distance cc dash is capital R minus small r theta, and this distance I dash is capital R theta, which means this extra distance of C to I, which means this extra horizontal distance from between C and I is actually small r into theta, right? So let's mark that as well. So this distance is small r theta. Okay, so let me just redraw the diagram. So if this is the instantaneous axis of rotation, and this is the center of mass of the disk, so 2 mg passes through this point. So the distance between, so the horizontal distance between I and the center of mass is small r theta. Okay, so now we need the distance of the point mass from I. So let's say the point mass is somewhere over here. Okay, so now earlier we figured out this distance was actually r phi, right? So the distance of, okay, which means the distance of small m mass from the ICR is going to be the difference of these two values. So now let's write down the torques. We can say the counterclockwise torque, which is 2 mg times its horizontal distance from I, which is r theta. This is greater than or equal to the clockwise torque, which is mg times its distance from I, which is going to be small r phi minus r theta. Okay, so once again, if you observe small m mass is at a distance of r times phi, and IC is at a distance of r theta. So the distance between these two is r phi minus r theta. Okay, so now we need a relation between theta and phi. Okay, so for that we can use the rolling condition. So we know for rolling, the velocity of the center of mass should be equal to r times omega, right? Here, if you observe, the center of mass is just moving in a circle of radius capital R minus small r. So, so the velocity of the center of mass, I can write it as capital R minus small r into theta dot. Okay, and what theta dot is? The omega with which this line is rotating. So the faster it rotates, the faster the center of mass moves. The rate of change of this angle theta is theta dot. Okay, so capital R minus small r theta dot should be equal to r omega of the disk, which, so the radius of the disk is smaller, and the omega of the disk is actually the derivative of phi, which is phi dot. So now you can just integrate this expression and we'll get a relation between theta and phi. So capital R minus small r times theta is small r times phi. So this relation is not based upon any approximation. So this is an exact relation. Okay. So now we can substitute phi over here. So we can cancel out the mg's. So this becomes 2r theta should be greater than or equal to capital R minus small r into theta minus r theta. So 4r should be greater than or equal to capital R. So from here we get small r by capital R should be greater than or equal to 0.25. Okay, so yeah, that was it for this question. So the complex part in this question is drawing a good diagram and writing the displacements. Okay, so I mean there is an energy method to solve this as well. So you write down the energy and differentiate it. But yeah, in that case you will have to consider the change in potential energy. So that is another level of complication. So you guys can try it out with that method if you want. But yeah, I like the torque method more than this. So now let's move to the last question. So if you guys are still watching, make sure to like and subscribe to the channel, and I'll be bringing more such videos in the future. Okay. So this question is also there in Pathfinder. It's there in the rotation chapter, I guess. So we have a bike whose length is L, having its center of mass in the middle, and it turns with a constant speed of v. V here is the speed of the center of mass of the bike. So to turn, the front wheel is rotated by an angle of theta. The coefficient of friction between the tires and the road is mu, and assuming the bike to be vertical and it does not skid, answer the following questions. So basically the tires of the bike is rolling, and the front tire is deviates by an angle of theta. So let's try to draw a diagram. Okay, so let's say this is the frame of the cycle. Okay, and let's say this denotes the handles. So here the main idea is that the front tire deviates by an angle of theta and the back tire is as such. Okay, something like this. So the center of mass of the frame is said to be at the middle, which means it's at an equal distance of L by 2 from both of the tires centers. Okay, so so in the question we have to figure out the radius of curvature of the center of mass of the bike and the net friction force acting on the bike. Okay, so now the main idea here is this angle theta is going to be a constant. Okay, so we have to treat it like a constant, which means the tire is always which means the relative position of the tires are fixed, meaning the back tire will be along the, you could say, the frame of the tire, whereas this tire is going to be always making an angle theta with the frame of the. Okay, so now as the relative, positions of all the equipments are fixed, we can treat the cycle like a rigid body. Okay, so now, and if it's a rigid body moving in a plane, then what we can do is we can always figure out an instantaneous center of rotation. So here, if you observe, we know the direction in which the front wheel is going to move, right? It's going to instantaneously move in this direction, facing this direction. So if I drop a perpendicular, so I'm going to drop a perpendicular, and I know the black, and I also know the back wheel is going to instantaneously move in the forward direction. So I'm going to draw perpendicular from the back wheel as well, and their intersection will give us the instantaneous center of rotation. Okay, so basically, now the advantage of the ICOR is that we can say that this tire over here will now move in a circle. The trajectory of this tire is going to be a circle, something like this. Okay, whose radius is let's call it r1. So the back tire is going to move along this circle of radius r1, and the front tire is going to move along the larger circle of radius r2. So with this, we can easily find out the radius of curvature of the center of mass, right? So now we can easily say that the center of mass, as it is a part of this rigid body, it's going to move along the circle with the green radius. Okay, so all we have to do is find out this radius. Let's call it RC. So these two lengths are equal, right? They're both equal to L by 2. Now this angle was given to be equal to theta, so this large angle will also be theta. Okay, so this angle over here is theta. So from this bigger right triangle, we can write r2 sine theta equals L, and r1 equals, or basically r2 equals L over sine theta, and r1 is L upon tan theta. Okay, so once we have these two informations, RC we can find out using this triangle. So we can just apply Pythagoras there. So we can say r1 squared plus L squared by 4 equals RC squared. Okay, and after a bit of further solving, we can find out the radius of curvature of the center of mass. Okay. Okay, so now the second question was asking us about the friction force acting on the particle. Okay, so now if we observe along the horizontal plane, the only force acting on the body is force of friction, right? Right, we can easily say that friction is the only force acting on the cycle. Okay, because the other forces are normal and mg, and which is in the vertical plane. Okay, so now the thing is, there will be friction in the front tire, acting on the front tire, and then there will be friction force acting in the back tire, both of which are going to be some different magnitudes, f1 and f2. Okay, but what they want is the total friction acting on the cycle. So for that, what we can do is we can use F equals ma. Okay, so we can just say that the net force in the horizontal plane is obviously just going to be the net friction force. So that will be equal to the mass times the acceleration of the center of mass. So we can use this logic to find out the total friction force. So for this, we need the acceleration of the center of mass. So if you observe now in the question, it was given that the center was moving with a constant speed of v. So which means, okay, so now obviously the v is going to be perpendicular to the radius. So v is in this direction. Now the thing is, v is a constant, so there is no alpha in this alpha for the circular motion. So the only acceleration is going to be centripetal, which I can write it as omega square RC towards the ICOR, right? Why? Because the center of mass is moving in a circle of radius RC. So its centripetal acceleration is omega square RC. Now here omega is the omega of circular motion. Okay, so it's the okay, so basically these two circles that I just drew. So the first circle is of radius r1 and the second circle is of radius r2. So basically the front tire moves on the outer circle and the green tire moves on the inner circle. Okay, and the center of mass moves on a circle that is intermediate. Okay, and the center of mass moves on a circle of radius rc. So here omega is basically the so now we have to figure out the omega for the circular motion. For that, we'll use the provided information that the velocity of the center of mass is v. So the omega of the circular motion is v divided by rc. So this is the rate at which, so if you connect the center of mass to the center of the ICO of the circle, let's say after some time it's over here, this angle delta theta it covered, we can write it as omega into delta t. Okay, so omega is basically the rate at which the angle is changing. Okay, and that we can obviously write as v divided by rc. And once we have that, we can write the acceleration of the center of mass as omega square times rc, which is v square by rc. Okay, and once we have the magnitude of acceleration of center of mass, we can write the net friction force as mv square by rc. Okay, and once we substitute the value of rc, we can get the net friction force in terms of theta, v and l. Okay, so yeah, the answers to these questions, so the answer to this question will be C, and so the answers to this question will be option C and option A. So that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe, and that's it. Thanks for watching.